not that many, maybe 20 or so. First of all, you have a particular pattern at the output here. What happens is that there is a small chance that the sequence of differences throughout this state here looks like that. As you see, a lot less red dots. In the beginning, a huge mess, actually quite complex to figure out what's going on there and what is supposed to go on there. But if something like that is possible, hash function is not good. That's what is called a differential attack. So the idea is to have a message, try the same message with just some bits flipped, and hope that you observe this particular sequence of differences throughout the state. If that happens, then you are already on track towards a collision. Well, as you saw, there were still some red dots at the end. So that's actually not a collision, but what you can do is to just have a second block. So that's the picture of before. The first block, we have a small number of red dots in the end. It's not a collision, but it's a near collision. The hash values only differ in a few bits. But what you can do now is to have a second block, the same message difference. In the beginning, a little different sequence of differences, but then the same sequence. What you end up with is exactly the same pattern of red dots in the second block. And you can hope that, because of this feed-forward operation here, you can hope that those differences cancel out. Near collision cancels the other near collision, but you can have a collision. And these are all rather theoretical ideas and concepts. There are lots of technical hurdles on how to do this. And in fact, until now it was not clear at all how to really do it. The computational complexity is to find a pair such that you have this funny behavior that not that many differences are in the state and differences are prevented to spread, is also rather high. What I'm here now doing is to announce that we actually started to do this just this week. So we did a lot of head scratching, we designed this attack, the difference we need, and we also optimized the method to look for this colliding pair of messages. So let me ask you, who has heard of BOINC? A few guys? Right. Who has heard of SETI at Home or Forwarding at Home, these projects? Yes, some more. SETI at Home is using BOINC. That's a distributed computing framework developed by some guys at Berkeley. So we are using this framework and send out work packages. You can think of this whole project as having 5 phases. The first 2 are more or less done. We finished to optimize the method to look for this SHA-1 collision for the first time. And now what we have is a huge workload we want to distribute. So you're invited to take a look and download this client. You can run it as a screensaver. However, there are lots of possibilities. However, that's a phase in the middle. Remember, we had this 2-block approach, which is kind of optimal, we found. Somewhere in the middle of the project, which will take several months, we will go ahead and design a new attack for the second block. And only then we can actually finish the search with a new distributed computing project, which is also looking for the second block, such that in the end, both near collisions we find here and here are expected to cancel out. Again, this will take lots of contributors and quite some time. In order to give you an idea on the difficulties people are facing, actually people are working on this already for several years, several research groups all around the world, and now the aim is to put an end on that. several aspects which influence the method. First of all, the choice of message difference. That's the first thing. But then the choice of the sequence of differences to follow is very non-trivial. This all interacts with the speedup method chosen. The way bits are flipped such that the search space is covered very efficiently. And last but not least, which is somewhat different to older hash functions like MD5, is that there's an issue with the degrees of freedom available. Means you can design an attack. However, if you don't have enough degrees of freedom to really search long enough, then even if the attack is good, you will never find a collision. And these things all interact and influence, in the end, the work vector. It's only recently that we got an understanding of how all these things interact. Now we put them to work. Well, let me conclude. Stop using MD5. There's absolutely no reason to use MD5 in new designs. A guy from Microsoft told me that alone in Windows, and Windows alone, there are several hundreds of places in the code where MD5 is used in code. So there's certainly quite some effort to be done to look at all of those and see where the problem is. So far, no one could show a collision for SHA-1. It's a rather big challenge because it doesn't happen that often that a very widely deployed cryptographic algorithm like this hash function, which is standardized everywhere, can actually be practically broken. And the nice thing is, you can be part of it. Just visit this website, download the client, and help crunching. Well, with that I conclude. Thanks for your attention. I guess we have time for questions. Please.
Just a short question. You were talking about SHA-1. How about the probability of collisions for the other SHA hashes you had at the bottom of your picture?
Well, they seem to be designed with similar attacks in mind. Means they are more resistant because of their design complexity I showed you. But the thing is, most of the new techniques we developed, we haven't applied yet to SHA-2. So it might well be that we make some progress there as well, but that's work to be done, we don't know.
For the moment they are
Yes,
safe.
For the moment they're safe.
Hello.
Hello?
Can you elaborate on how you find a collision from two near collisions?
Sure. Shall I go back to the slide? Okay. So near collision, that's the first block. We look for a long time and find a message pair that only has, in this case, 2 or 3 bits that are different at the output. These differences are now copied to the input of the next block. And this makes the attack different, and hence a new phase is needed to design a new attack for this phase. But if you manage to incorporate these additional differences, which you don't have at the bottom because you start with 0, if you manage to incorporate them and still follow the same sequence of differences afterwards, and still manage to have the same difference at the output here, then what happens is that you always have this feed-forward operation, that meaning the differences here go here and are added. That's a model addition here, actually. And after then, there's a chance that these differences cancel out via this model addition operation.
So you don't actually need them to be near collisions. They just have to be the same,
well,
different.
It doesn't help if they are completely independent, these near collisions. So if we have a particular near collision here, we need a matching near collision at the second block. Only then those cancel out. Yeah.
And you're looking for near collisions because they're easier to find?
Exactly.
Okay, thanks.
In theory, it would also be possible to look for a sequence of differences that already collide here. But it turns out, after a lot of head scratching, that that cannot be more efficient than such a two-block approach. That's why we are doing that.
Thanks a lot.
Is this on? I was wondering, at BOINC, will you have both x86 and AMD 64 support on your clients for both
Well,
Windows
so
and
far
Linux?
we have binaries for Windows and Linux, but only for 32-bit platforms.
Okay,
But we will continue to support more platforms.
okay, I'll join that.
Right, great.
These attacks attack the message expansion, but is it possible to attack the message compression part also?
Well, actually, the attack work on both. It's expansion and compression. Only we work with the interaction of both building blocks. So the message expansion is an important part here. We use some properties in the attack, but we also use the fact that the compression has a certain structure.
So actually the major thing that we use hashes for and that we worry about for collisions is message authentication. So why exactly are we still bothering with MD4 derived algorithms when there's modern things like I think UMAC is provably unconditionally secure, and as long as AES is secure. So
It's a very good point.
Do you have anything to say about other approaches?
Well, the thing is, hash-based MACs were very popular in the middle 90s because fast hash functions were around. They were much faster than the available block ciphers. DES, the block cipher back then, was optimized for hardware. On your 32-bit machine, it was rather slow. That's why hash-based MACs turned out to be very, very popular. They went into internet standard. That's why they are still rather important. But indeed, there's other technology available based on block ciphers, which is now state of the art.
What options do we have if char is actually broken? Are there other hash functions you would recommend, like Tiger 192, or do they have the same problem?
Well, the area of hash function design and analysis is a very active one. In particular, in the case of Tiger, no one looked at it for quite some time, but since 2 or 3 years, people started to look at it, and indeed also there weaknesses were found. The other alternatives, like Whirlpool, which are already around for quite some time, seems to be very robust and conservatively designed. However, the organization which standardized this SHAs, SHA-1, and also the SHA-2 family, is planning to create a new standard, which means this will be a multi-year effort to ask the research community for proposals. They will be evaluated similar to the AES process, and in the end, in maybe 4 years or so, a new hash function will be proposed and standardized based on all the insights we gained so far.
Is the combination of two hash functions still secure if both hash functions are insecure?
Well, you don't gain a lot. It's a little fail-safe practice. But if you want to be kind of efficient, that's probably not the best way.
Okay.
Over the last year, much effort was put into the development of efficient implementations of hash functions based on block ciphers. are these more secure